Okay, so this lesson is going to be on finding the planes associated with the tangent, the unit normal, and the binormal vectors. Um, so here's the example. Now, oh, actually, let me do this first. So if we had those three vectors, remember they're all orthogonal to each other. T, N, B, and they form that TNB frame. Now there are three planes that get formed here. So there's this plane formed by T and N. There's the B and N plane formed here. And then there's this plane formed by B and T, or defined by B and T. And so they each have a name. The one that is formed by the tangent and normal vectors, or the unit tangent and unit normal vectors, is called the osculating plane. The one formed by the binormal and normal vectors is called the normal plane. And then this one over here, formed by T and B, is called the rectifying plane. Okay, so the example that we're going to do is find the normal, osculating, and rectifying planes. Or plane equations, let's say. For R of t equals t squared, t cubed, corresponding to t equals 2. Now, note when t equals 2, we have R of 2 equals the vector 2, 4, 8. So we want the three planes. The three planes passing through the point 2, 4, 8. So that's the same thing as saying, like, this point right here is the point 2, 4, 8. And then we've got that curve that just passes through it, and these would be the three planes formed there. Okay, so kind of a refresher, recall that the equation of a plane can be found by using the equation ABC dot x minus x naught, y minus y naught, z minus z naught equals 0. Right. Let me make this screen a little bit bigger. Okay. And in this case, ABC is any vector normal or perpendicular to the plane. And this is a general vector in your plane, but the x naught, y naught, z naught is going to be any point in your plane. Kind of like point slope form when you think about it. Okay, now in our case, we only know one point in the specific, in all three planes. It's 2, 4, 8. So this is going to be 2, 4, 8. All right, so the vector, let's do the normal plane first. All right, so the normal plane is formed by B and N. And so if we need a vector that's perpendicular to it, that would be T, because these guys are all perpendicular to each other. So really, we're going to use T. So let's write this. A vector perpendicular to the normal plane which is defined by b and n, is at r of 2 is t of 2. Right. Now that we're at t equals 2, I can say that this would be t of 2, n of 2, b of 2. Okay. But note, we can also use as a perpendicular vector any vector that's pointing this same direction, or the exact opposite direction, which is called parallel. We can also use any other vector parallel to t of 2, like r prime of 2. Or some easier, like if r prime of 2 was every term was over 17, well, then just get rid of that, because if we multiply all the components by 17, you just get a vector pointing in the same direction. Okay, so let's find r prime of t. That saves us a little bit of work. So first we'll find r prime of t. And let's see, r of t was t, so 1, and then t squared, and then t cubed, so 3t squared. There's the derivative, which means that r prime of 2 is going to be 1, 4, and 3 times 4, 12. Okay, so this points the same direction as t of 2. Okay, so we can use that as our normal vector. So therefore, the equation of the normal plane is going to be given by ABC, which is 1, 4, 12, dot x minus 2, y minus 4, z minus 8 equals 0. And then if you work that out a little bit, you end up with x plus 4y plus 12z. And then if you multiply out all the constants and move them to the other side, you get 114. So there's the normal plane. Okay. That one's going to be the easiest one every time, because the perpendicular vector you get to use as your ABC is the tangent vector, the unit tangent or anything pointing that direction, which is directly based on the first derivative. Everything else after that, anything that uses n as the perpendicular or b as the perpendicular vector, those are going to be harder because you'd have to calculate n or b, which requires t prime divided by its length. So that's significantly worse. And to prove it, we'll do it. So let's do, let's do the rectifying plane. So a vector that is perpendicular to the rectifying plane. Let's see. So the rectifying plane is the one formed by B and T. So n would be perpendicular to it. Is n. Or any vector parallel to n. And we care about at 2, so I'll say n of 2, or any vector parallel to n of 2. So we'll start calculating n of 2, and then if we see that we can get rid of certain values but still have a vector pointing the same direction, that's what we'll do to keep stuff simpler, because this gets ugly pretty fast. So let's take a look. T of t. Now we have t of t from before. Oh, no, we don't. We just have r prime. So r prime of t was 1, 2t, 3t squared. T of t is going to be r prime divided by its own length. So I'll write that here, r prime of t divided by the length of r prime of t. So that ends up being 1, 2t, 3t squared divided by that length, which is the square root of 1 plus 2t all squared, 4t squared, plus 3t squared squared, 9t to the 4th. Okay. So let me put the non-vector part in front. 1 plus 4t squared plus 9t to the fourth. And then over here will be the vector part. Okay, so in order to get the normal vector, we need the tangent derivative, the unit tangent derivative, divided by its length. Remember, that's the definition for the unit normal. Okay, this is going to stink, but here's what we're going to do. This right here, I'll use a different color to highlight it. This right here is a regular function of t, a single variable function of t. This guy right here is a vector function of t. So when we take the derivative to get t prime, so t equals f times u. I realize that doesn't look great, but oh well. T prime is going to be the product rule of this. F prime times regular u plus f times u prime. Now, remember, these are all functions of t. U prime is still going to be a vector times some sort of function that represents a scalar. This one's a vector times some sort of function that represents a scalar. So together, that still forms a vector. And then we can take its length. So let's see what we get here. I'm going to do, before I plug in, I don't want to just do this all at once. I'm going to get t prime of t by itself first. So f prime, this thing right here is the same thing as 1 plus 4t squared plus 9t to the fourth to the negative 1/2, that whole fraction here. So then the derivative will be negative 1/2 1 plus 4t squared plus 9t to the fourth to the negative 3/2 times the derivative inside, which would be 8t plus 36t cubed. So that's the f prime part. And then times u, 1, 2t, 3t squared. And then plus, and then regular f, so I'll leave that like this. 1 plus 4t squared plus 9t to the fourth times u prime, at least u prime is easy, it's 0 to 6t. Okay, so again, this part right here is the f prime of t. This is u of t. I don't know what that is. U of t. This is f of t plus, and this is u prime of t. Okay, so now n of 2, if I replace the t here with 2, n of 2 is really t prime of 2 divided by the length of t prime of 2. So instead of trying to find the general vector t prime's length, let's just plug in 2, and we can avoid having to deal with the length of this hideous looking thing right here. So t prime of 2, that's still bad enough. So if we work that out, that's going to be negative 1/2. 1 plus 4 times 2 squared plus 9 times 2 to the fourth to the negative 3/2. So I'll tell you that this part on the inside of the parentheses is 161 to the negative 3/2 times, and then 8 times 2 plus 36 times 2 cubed is 304. And then this vector turns into 1, 4, 12. Plus, and then 1 over root 161. And then 0, 2, and then 6 times 2 is 12. Okay, so let me simplify this part over here. Let's see, the negative 1/2 times the 304 turns into negative 152. And then the 161 to the negative 3/2 turns into 161 root 161, right? Because that's the 2/2 is the 161, and then the extra 1/2 is the root, times 1, 4, 12. plus 1 over root 161 times 0 to 12. All right, now that's t prime of 2. I could keep simplifying if I want to, but remember I just need a vector that is parallel to that one. Is that right? Yeah. In fact, I don't actually need the length of t prime. I just need a vector pointing the same direction as n. Well, it doesn't matter how long t prime is, right? T prime divided by any length is going to be a vector pointing that same direction. So I just need t prime of 2 or some vector that points the same direction as t prime of 2. Okay, so let's see. So here, I'll add up here, is n of 2, or any vector parallel to n of 2, like t prime of 2, or some vector easier to use than t prime of 2. So here's t prime of 2. Why don't we do this? So I'll write here, we just need a vector parallel to this one. So let's just multiply everything by 161 root 161, and that'll get rid of all of my fractions to get an easier to use vector. So then in that case, the perpendicular vector that we find here, vector perpendicular to the rectifying plane. Well, that would be, let's see, if I multiply everything by 161 root 161, the first term turns into just 152, 1412. And the second term turns into 161, 0212. Then if we add those together, you end up with negative 152, negative 286, 108. I can simplify that even more. So another vector perpendicular to the plane would be if I take these guys and divide them all by 2 or negative 2. So if I divide them all by negative 2, I get 76, 143, and negative 54. So that's a slightly easier vector to use. So let's use this guy. So therefore, the rectifying plane equation can be given by 76, 143, negative 54, dot x minus, and then the point that we're going through again is 2, 4, 8. So 2, y minus 4, z minus 8 equals 0. And if you work this out, you get 76x plus 143y minus 54z. And then if you get all the units onto the other side, it ends up being 292. Right there. Okay, so we got one more plane left. So the last plane here, so the last plane is the osculating plane. Now, an osculating plane, the main vector that's going to be perpendicular to it is the binormal vector, right? So we want perpendicular vector to plane, which is like the binormal vector or any other vector parallel to it. Okay, so we could use B of 2, which we know is T of 2 cross N of 2. That's the definition of it. But I also know that a vector pointing in the same direction of T is R prime of 2. And I know that a vector pointing in the direction of N was the 76, 143, negative 54. So I could just use those two vectors. So the two vectors that I used in the previous problems. So let's see, where's one of them? 1, 4, 12, and 76, 143, negative 54. The two easiest vectors you could ever think of. Or use 1, 4, 12 cross 76, 143, negative 54. So this one equals, and I'm going to do a determinant style. So here's I, J, K, 1, 4, 12, 76, 143, negative 54. So let's see what happens here. From here, I just go straight into the vector usually. So if I'm looking at the I term, it's 4 times negative 54 minus 12 times 143. And then the next term is going to be a negative. So if we get rid of the J column, it's 1 times negative 54 minus 12 times 76. And then the last term, the K column, is just normal derivatives, or normal determinant, 1 times 143 minus 4 times 76. Oops. And so then this comes out to be, let's see, negative 1932, positive 966, and negative 161. Now, those are all divisible by 161. So we can actually use a simpler version of this vector by dividing negative, let's make it negative 161. So that gives us the vector, let's see, what does that come out to? 12, negative 6, positive 1. Okay, so that's going to be our perpendicular vector that we're using for the osculating plane. So the osculating plane equation is given by 12, negative 6, 1, dot, x minus 2, y minus 4, z minus 8, and that has to equal 0. And if you work that out, you end up with 12x minus 6y plus z equals 8. So I think that the hard part is getting that second plane. The first plane's always easy if it's going to be the normal plane, because then that vector that you can use is just r prime. The second vector is always, the second plane is always going to be annoying because you have to find the normal vector, the unit end vector, which is a pain a lot of the time. But a lot of times there's sines and cosines involved, and you end up canceling stuff out or getting 1 when you add them. The third vector, the third plane, if you've already found the other two, you don't have to go through the B. You can just find something pointing the same direction by using the two normals that you found earlier, the two perpendiculars that you found earlier, and cross-producting them to get a third one. Okay, I hope that helps a little bit. I will show you one other thing here. That applet from a previous video that I found, I actually graphed this 3D function. It's t squared t cubed. And if you look at it, one thing that's interesting, I think, if you ignore the y, then it's like xz plane. If you look at it, that would be z equals x cubed, and there's the function right there. You can easily see that cross-section looks just like z equals x cubed. If you ignore the z, then you get y equals x squared. So let's see, can I get that one? So now I've minimized the, we're staring straight down the z-axis, and you can see that it's a parabola. But if you look at it in 3 dimensions, it's this kind of spirally thing right there that goes upwards. And so What this does, this as I move the t value up, you'll see that binormal, normal, and tangent vectors come around. Let's see, where is it? There it is. Okay, and you can kind of see that the tangent vector, let me go back down. The tangent vector is always pointing at the way that the particle is moving around the curve in that direction. The normal vector is always pointing inwards along the curve, right? Can you kind of see that there? And then the binormal vector is always just pointing perpendicular to it, to the other two vectors. Okay? So what we did was we found when t equaled 2, of course that's not going to show up here. Here. So let's say we were looking at like t equaled 1 or 1.6, right? So what we found were the 3 planes defined by these 3 different vectors. Okay? All right, I hope that helps a little bit, and I'll see you guys soon.